So in this section, we are going to be discussing some integrals that result in inverse trigonometric functions. So real quickly to review, I wanted to talk about three particular derivatives of inverse trigonometric functions. So first one is going to be the arcsine function. So the arcsine function, its derivative is going to be 1 over the square root of 1 minus x squared. As such, it only makes sense to say that if we were to take the integral of 1 over the square root of 1 minus x squared dx, that the result would be the arcsine function, plus a constant, as is consistent with our indefinite integrals. Additionally, if I were to take the derivative of the arctangent function, that would be 1 over 1 plus x squared. As such, if I were to take the integral of 1 over 1 plus x squared dx, this should result in the arctangent function, plus a constant. And finally, if I take the derivative of the arcsecant function, this would be 1 over x times the square root of x squared minus 1, letting us know that if we were to integrate 1 over x times the square root of x squared minus 1 dx, that this would be equal to the arcsecant function plus a constant. Now, we're not always going to have the good fortune that each of these denominators has exactly a 1 in it. Sometimes it'll be some other number. So how would we deal with something like, going from the first case, what if we had 1 over the square root of a squared minus x squared dx? So maybe something like 4 minus x squared or 9 minus x squared. Well, this can actually be done using a substitution. We are going to let u be equal to x divided by a. Or similarly, if we were to solve this for x, x would be equal to a times u, where a is our constant and u will be our variable. That way, dx is going to be equal to a times du. Now, what I'd like to do is actually perform these substitutions into our integral. So this will be 1 over the square root of a squared minus, and then instead of x, we're going to call that au, because this substitution is gold. Then dx would be a times du. Now, in the denominator, each of the terms inside of the radical will now have an a squared in common. So, if I factor out that a squared and toss our coefficient of a in front, I can then take the square root of this a squared and wind up with an additional a in the denominator, giving us a times the integral of 1 over the square root, 1 over a times the square root of 1 minus u squared du. Now the a that we had from earlier and this a should cancel each other out, leaving us with, after our substitution, exactly what we had from earlier, simply making use of u's rather than x's. That lets me know that this is going to be equal to the arcsine of u plus a constant. But we also know that u is equal to x over a, which lets us know that this is going to be the arcsine of x over a plus a constant. Now, I would like to let you know that there is something similar that you'll see for the other two forms as well. This is where I'm going to ask you to try this out at home. If you have the integral of 1 over a squared plus x squared dx, and you do the exact same substitution, x equals a times u, and dx is equal to a times du, you are going to wind up with, and you feel free to check this one out for yourself, one over a times 1 over 1 plus u squared. So upon integrating and substituting back, you'll have 1 over a times the arctangent of x over a. plus a constant. Now, the reason that we wind up with an extra a in this one is due to the fact that there was no radical to simplify this a squared from back here into simply an a. You will wind up with an a squared in the denominator. That's why there's the extra 1 over a at the end. But again, try this out for yourself. Additionally, if we were to do 1 over x times the square root of x squared minus a squared dx, and apply the same set of substitutions, x is equal to a times u, and du is equal to a times du, you are going to wind up with 1 over a times the integral of 1 over u times the square root of u squared minus 1 du, letting you know that you will get exactly 1 over a times the arcsecant of x over a plus c. These formulas can also be found in the book, but for now you may use all three of these, this one for this shortcut, this one with this shortcut, and this one with this shortcut as the shortcuts that they are.